Hey everyone, we are starting a new chapter today. This is chapter 13, and it's about homomorphisms. All right, so we've learned what a homomorphism is, but we have not done a whole lot of work with homomorphisms, and so now we're going to do an in-depth study of homomorphisms and how they help us in our understanding of group theory. So, just as a reminder, so recall, a function, let's say it like this. So a homomorphism from, let's say, group G to group G prime is a function, say capital phi, from G to G prime, such that phi of, I don't know what symbol I want to use here, G hat is equal to phi of G times phi of G hat for all little g and little g hat in capital G. And so a homomorphism, that's the end of the definition, of course. A homomorphism then is a structure-preserving map between groups. So this is just kind of paraphrasing this. So a homomorphism is a structure preserving mapping between groups. Now, what do I mean when I say structure, the group structure? What do I mean? Well, when we study groups, what are we doing? We start off with a set, and a set is as structureless as it can get, right? It's just a blob, right? Just some elements. That's it when we talk about sets. And so when we talk about a group, now we have structure, and that structure is that you're able to do certain things with the elements, right? There's this notion of multiplication, right? There's this property that's on top of the fact that it's being a set, the structure. So when I say the word structure, it is additional properties that the set has, right? When we talk about a group, it's a set together with a binary operation that satisfies various axioms. And so a homomorphism respects the structure, right? We have multiplication going on inside, we have multiplication going on outside. And so a homomorphism is a function, a mapping between groups that says you can multiply inside G and then apply the homomorphism, or you can apply the homomorphism individually and multiply inside G prime, and you're going to get the same thing. All right, so it allows you to transfer the structure from G to G prime. Now, and so I kind of want to just sort of riff on this topic for a minute. So, just kind of thinking about the classes that you've taken, right? And let's start off, we're doing group theory right now. So what is group theory? Group theory is not just the study of groups. It's the study of groups together with their structure-preserving maps. So group theory is really the study of groups and homomorphisms. And what I want to do, sorry, I ran out of room there, but that says homomorphisms there. So I kind of want to just kind of create an analogy, looking at the other study classes that you studied. So how about linear algebra? What is linear algebra? Well, it's the study of vector spaces together with their structure-preserving homomorphisms, their structure-preserving maps, which we call linear transformations. And so linear algebra is not just the study of vector spaces, it's the study of vector spaces together with linear transformations. Let's think about other classes that you may have taken. Complex analysis. Maybe taken 408, 409. So complex analysis. So what do you study? Well, obviously study complex numbers, but you also study the mappings that respect the complex structure. And what are those called? Those are called analytic functions. Sorry. Analytic functions. Let's see, other things. Oh, how about real analysis? What do you study in that class? Well, of course, you study R, but you also study either continuous or differentiable functions. So we'll say continuous or differentiable functions. But both of those pay attention to the structure of the set R together with the properties of the real numbers. Oh, geometry. When you're studying geometry, so geometry is the study of sets that have a notion of distance, right? So let's say sets with distance, right? So these are the set together with the structure, this notion of distance, and then often these are metric spaces is the official term for this, sets with a notion of distance. And then isometries are the mappings between metric spaces that respect distance. Sorry, I ate some peanuts and now it's just like something stuck in my throat. Topology is the next thing. So if you've taken topology, I guess you probably can't take, oh no, you could take topology. If you've already had analysis, you could be taking topology right now. And so topology is, well, it's the study of topological spaces together with continuous maps. Right, topology is basically the best place, the standard place to come up with a notion of continuity. What else? Oh, yeah, I guess that's a good place to stop. But here's the idea: is you can ask the question, what do we do in mathematics? Right, your friends might say, okay, what do you do? You're a math major. What are you doing in that? And you say, well, I'm taking a bunch of math classes. Okay, in each of those math classes, think about what you've done. In many, especially the theoretical type classes, I mean, there's some obviously applied classes where this may not quite work. But what do we do as mathematicians? Well, we study sets with structure together with the maps that preserve the structure. And so hopefully you can see sort of a pattern going on here. When we study mathematics, we want to study sets, structured sets, together with the maps that allow us to transfer between various sets with the same structure. Oh, and here's maybe one. Here's another plug for group theory. So let's just say, as an interesting note, right, so in all of these contexts, in each of these different subjects, what we have is we have groups together with structure-preserving maps. Something, structure-preserving maps. So anytime if you were to then focus on the structure-preserving functions between whichever of the categories we're working here, so we'll say it like this, so suitably defined, the set of structure-preserving maps forms a group. So, for example, the set of all homomorphisms from one group to another forms a group. And so then you can study the group of homomorphisms. Same thing with linear transformations, analytic, continuous, all of these all form groups that allow you to then get a deeper understanding of what you're working with, what you're studying. Now let's look at some examples of homomorphisms. And I want to kind of go through some of the standard, the big common, well, I should say big, but the common homomorphisms out there that will come up, and we'll need to make use of some of these. In fact, all of these. So, examples of homomorphisms. So the first one, the trivial homomorphism. Hopefully those of you with a sort of philosophical frame of mind are ignoring what I was saying right here, and you're still focusing on this. This is amazing, right? This not only tells you that group theory is an important subject to know, right? But it really, I don't know, just, well, I don't know. You should be meditating on that. Although pay attention now, meditate on that later. So the trivial homomorphism, if G and G prime are groups, then what we have is what's called the trivial homomorphism. Let's say let phi from G to G prime be defined by. So what we're going to do is we're going to say phi of little g equals the identity in G prime, right? So what it does, and we'll say here for all little g in capital G. Take everybody over here, send it to the identity. You can check, and I'm not going to verify any of these. I'll let you go through the details, right? But it turns out that this is a homomorphism. The next one, this one has a name, I think it's called the signum. Or the sign, or this is, what am I doing here? I want to say signum, but it doesn't matter what the name is. I think it's called the signum function or the sign function. It doesn't matter. What do I want to say? Oh yeah. For n greater than or equal to 2, let, don't use a symbol here, let's just call it phi, from Sn to Z2 be defined by phi of a permutation sigma equals, well, there's two possibilities. It'll either be 0, and it'll be 0 if sigma is even, and it'll be 1 if sigma is odd. And when I say even or odd, I mean expressible as an even number of transpositions or an odd number of transpositions, exactly what we talked about before. All right, so it turns out that this is a homomorphism. And you should verify this, right? You should go through the details. The next one, this is called evaluation. So let's let F, capital F, be the set of all functions from R to R. Of course, now under function addition, it turns out that capital F is a group, so let's write that. So under function addition, capital F is a group. And now let's define, so let's choose a real number. So for little c in capital R, define phi sub c from F to R by phi sub c of the function f equals f of c. All right, so this is called evaluation at c. So phi sub c is called evaluation at C. And this idea of evaluation is going to become important, especially when we move on to Math 42. Next one. Determinants. So if we take a couple of matrices, so let's say if A and B are in G, L, and R, then the determinant can be viewed as a function. Well, okay, so let's say it this way. Let's say it like this. Determinant of AB, here's a property that you learn in Math 206 or 306. Determinant of AB is determinant of A times determinant of B. Now, what's going on here? Well, what you do is you are plugging in a couple of matrices. When you compute the determinant, you get a real number. So you can view the determinant. So we can view the determinant because of this property right here. We can view the determinant as a homomorphism. Homomorphism. Which we usually write just as DET, and it goes from GLNR to R. Right? So there's a sort of more advanced way to think about the determinant, in particular with respect, or with respect to this particular property. What it is saying is that the determinant is a homomorphism. And then I got a few, three more. So next one is multiplication by n. So this one's kind of obvious, but it turns out to be important. So the mapping phi sub n from z to z defined by phi sub n of little a equals n times a. It turns out that that's a homomorphism also. So you can check that. And then two more. So the next one is called projection. And so what do we got? Let's say G and H. So if G and H are groups, then pi, let's put it down here, pi sub G going from G cross H to G defined by pi sub capital G of little g comma little h equal to little g. This has a name, so this is projection onto G. There's also projection onto H, right? Put a capital H here, and then the output would be little h right there. That's also a homomorphism called projection onto H. And then one more. So number 7, this is reduction mod n, and it goes like this. So we have phi from z to zn defined in the obvious way, so defined by phi of little a equals a mod n. This is called reduction mod n, and it turns out that this is a homomorphism. And I mean, maybe I should be a little bit careful here. Who is this, right? A mod n, when we write this, it is, yeah, I should be a little bit careful here. So where A mod n is the unique R in the set 0, 1 up through n minus 1, such that A is equal to Qn plus R. So this right here, when we write, this is the sort of the computer scientist notion of mod, right? It's the remainder that you get when you run the division algorithm on A. Okay, so there's some examples of sort of famous or important homomorphisms. We'll come back and we'll see every single one of these at one point or another in this class. See what time we got. Okay. Okay, so next I'd like to state a theorem here. And I want to call this properties of homomorphisms. Oh, and sorry, I didn't give it a number. This should be theorem 13.1. Theorem 13.1, properties of homomorphisms. Now, okay, so let's let phi from G to G prime be a homomorphism. There's going to be 5 pieces to this, and you will have seen some of these already. So the first one, phi of E equals E prime. And I guess I should say then. So what does this say? A homomorphism takes the identity to the identity. We already know this one. And what I want to do is I want to collect a bunch of properties of homomorphisms together and have them all under sort of one umbrella. What's next? Part B. For any little g in capital G, phi of G inverse is equal to the inverse of phi of G. Oh, I just put that in the wrong spot. Inverse of phi of G. We've seen this one also. Homomorphism take inverses to inverses. More generally, for any little g in capital G and integer little n, phi of G to the n is equal to phi of G raised to the n. Once again, we've seen this one. The next one, so part D, if H is a subgroup of G, then phi of H is a subgroup of G prime. So we've seen all 4 of these so far. I just want to put them into the homomorphism chapter as part of a theorem, right? So homomorphisms take identities to identities. They take inverses to inverses. They take powers to the same powers. They take subgroups to subgroups. And then the last one, and this is the first one that that we haven't seen. we'll put it here. So part E, if H prime is a subgroup of G prime, then the inverse image of H prime is a subgroup of G. So the inverse image of a subgroup is a subgroup. Now, for the proof, all right, so we've already seen the proofs of A through D. So we have already proved parts A through D. Right, so it just remains to prove part E. Okay, so what do we need to do? We want to show that the inverse image of a subgroup is a subgroup. So, well, how do we show that things are subgroups? We use the subgroup test. So, to prove E, we first note that little e is an element of the inverse image of H prime. Why is that? Well, this follows from the fact that phi of E needs to equal E prime. E prime is the identity in capital G prime, which must live in H prime, because H prime is a group, or a subgroup if you like. Right? So the point is phi of E equals E prime, which is an element of H prime. Right? There's the reasoning there. All right, so that tells us that it's non-empty. So now let let's say A and B be elements of the inverse image of H prime. So then phi of AB, which equals phi of A times phi of B. Now, because A and B are in the inverse image, that means phi of A is in H prime, phi of B is in H prime, so this is in H prime. And so AB is in the inverse image. That's just by definition of what it means to live in the inverse image. Also, what do I need now? I've shown that it's closed under multiplication. I need to show that it's closed under inverses. And so what do I need to do there? I need to look at phi of A inverse. That's equal to phi of A inverse. Because phi of A lives in H prime, so does its inverse, because H prime is a subgroup, which means that it's closed under inverses. So that's in H prime. Thus, A inverse is in phi inverse of H prime. So, by the subgroup test, phi inverse H prime is a subgroup of G. All right, so that completes the proof. Okay, so the next thing I want to talk about, we need this definition here. So let's let phi from G to G prime be a homomorphism. The kernel of phi is, well, it's the set which we would just write as KER of phi. So the kernel of a homomorphism is the set of all little g in capital G such that phi of G is equal to E prime. So it's the set of all elements in the domain that get sent to the identity in the codomain. Now, okay, so there's the definition. Right? The kernel is the set of all elements that get sent to the identity. Now, since E prime is a subgroup of G prime, right? The identity in G prime, or the group, the trivial subgroup in G prime is a subgroup. And if you notice, the kernel of phi, essentially by definition, is equal to the inverse image of E prime. By our previous result, right, it follows that the kernel of phi is a subgroup of capital G. So the kernel of a homomorphism is always a subgroup of the domain, right? And this follows, this is just by part E. So this is 13.1 E. It's just by recognizing that this definition right here is equivalent to saying that the kernel is the inverse image, right, of the trivial subgroup. Right, so that's an easy way to see that the kernel actually is a subgroup of the domain. So that's going to be very important, right? We're going to use that fact quite a bit. So the kernel of a homomorphism is a very important subgroup, right? So whenever you have a homomorphism, you've got a kernel. And yeah, I think, well, yeah, the next thing I want to say here, so as a corollary to our previous theorem, so this is corollary 13.2. A homomorphism phi from G to G prime is 1-to-1 if and only if the kernel of phi is trivial. Now, if you think back all the way to Math 248, you learned how to show whether a function is 1-to-1 or not. And there's this sort of set theory way to do it. And there's nothing wrong with that, right? I mean, that's still sometimes what we'll use in group theory, but more typically, almost always now, in this class, when we want to verify that we've got a 1-to-1 homomorphism, right? Because we have the power of being a homomorphism rather than just a function, this will be what we will do. We will verify that the kernel is trivial. Right? So almost always, when you're working with groups, this is the way to show 1-to-1-ness rather than the set theory, the Math 248 style of doing it. So, I mean, there's something to prove here, and this is an if and only if statement, so we need to go both forwards and backwards. So let's assume, in the forward direction, let's assume that phi is 1-to-1. Okay, so now we need to look at the kernel, and so if G in capital G is such that phi of G is equal to E prime, then what do we know? Well, we know that phi of E is also equal to E prime. Because we have a 1-to-1 function, it forces us to conclude that G is equal to E, right? So then, I don't want my comma there, So if that is equal to E, then since phi of E is equal to E prime, we conclude that G is equal to E. In other words, the only element that gets sent to the identity is the identity. Right? The kernel is trivial. In the reverse direction, so for the reverse direction, so now let's assume that the kernel of phi consists of a single element, just the identity. So the only element in G that gets sent to E prime is little e. So now we want to show that it's one-to-one. So let's let x and y be in G such that they give us the same output. So such that phi of x equals phi of y. Right? So then, well, let's see. Let's look at phi of xy inverse. That's equal to phi of x times phi of y inverse using the homomorphism property. And then using our previous theorem, we know that this is phi of x times phi of y inverse. But then looking at this equation right here, we know that this is equal to the identity. All right, so that's got to equal E prime. So that tells us then that xy is in the kernel. Thus, sorry, I said xy. I meant to say xy inverse. Xy inverse is in the kernel of phi. What do we know about the kernel of phi? It's equal to the trivial element, or the trivial subgroup. So it follows that, now this is kind of fun, the way this works out. So what does it tell us? It tells us that xy inverse equals the identity. Xy inverse equals E, and so x is equal to y. Therefore, phi is 1-to-1. That's the end of the proof. So remember what I was saying. This is the typical way that we show that homomorphisms are 1-to-1 when we're working in group theory. How are we doing on time? I guess this is a good place to stop. So we'll pick up with this idea and make use of it in the next lecture. Okay, so we'll see you then.